So this is the audio lecture finishing up on the lecture on validity for seminar in personnel psychology. So we left off on various methods to basically measure construct validation. So we just finished multi-trait, multi-method matrix. Another version is simply known group differences. Basically, known group differences is, again, instead of making a single correlation, we're now actually testing hypotheses of what the construct should and should not predict. So this is often viewed as also an ANOVA approach. So the hypotheses are often going to be to the nature of top performers should be highly rated in this, bottom performers should be lowly rated, people that stay with the company for a longer period of time should be highly rated, and whatever the construct is, people that leave quickly should be lower rated. In other words, it's kind of turning it back on itself, and instead of us trying to predict individual correlations, we're now actually looking for known group differences. So, for example, if we have a construct that we're trying to measure that we expect to be related to tenure, related to performance, we look at the IVs in the ANOVA being top, middle, or bottom performers, or high tenure versus low tenure, and we're looking for statistically significant differences then in our actual construct. Another method we can use in construct validation is factor analysis, which is basically a statistical technique for examining the underlying dimensions within a test. And this is especially useful if we have a multi-construct or multi-subgroup test. So, for example, if we have a general cognitive ability test, but we anticipate that there is going to be additional factors, mathematical ability, spatial visual ability, verbal ability, we would actually test to see, does those beliefs pan out? Do we actually find statistical, numerical information that suggests that there are, in fact, these subscales? So generally, a factor analysis is looking at a couple of things. It is looking at the intercorrelational matrix. So, for example, we've got vocabulary here. That's number one, going down the vertical axis. It's related an R of 0.22 to algebra, an R of 0.20 to geometry, but it's more related to analogies, 0.77, and the word problems in algebra, 0.50. Likewise, algebra, number 2, is not highly related with analogies, 0.21, but is related to geometry, 0.65, and somewhat related to algebra word problems, 0.48. But a factor analysis goes beyond just looking at the intercorrelation matrix. It also asks the question, what are the total number of factors that explains the majority of the variance? And from that, we actually get factors. And factors are usually based on not explaining all the variance, but explaining more variance than any single item would by itself. So if a factor was going to explain less than any one item would explain by itself in the model, we're not going to look at that factor. And in fact, the evidence that we get here is not just that they're interrelated, that there's actually broadly two underlying factors in this particular cognitive ability test. That there's factor 1, where vocabulary loads heavily, 0.92, and analogies load very heavily, 0.93. And then there's a second factor where algebra loads 0.88 and geometry loads 0.89, and these are called factor loadings. Now notice that algebra word kind of loads onto both, but actually slightly loads more on the vocabulary one than the mathematical one. So this would be a good example of, even though we have multiple subsets, that broadly speaking, the construct validity here is we have a overall construct, general cognitive ability, with two primary factors, one of them quantitative and one of them verbal. So just broadly, an overview, content validity deals with whether the assessment, content and composition is appropriate given what is being measured. It really refers to, is there an appropriate representation of questions from the entire topic area or pool of questions you get asked to get at the construct that you're interested in just through the content of the questions. It is related to face validity, and face validity is often a method to determine if you have content validity, but remember, we can have content validity without face validity. Then we talked about criterion validity. I kind of phrase it as more of our practitioner side, as we're mainly looking at whether we have evidence that our new measure is predicting a criterion or an outcome in the workplace that we think is valuable. And then finally, construct validity, an overall assessment of whether the measure is correctly actually measuring a construct. Is it a trait? Is it an attribute? Is it an ability? Is it a skill? And is it interrelated with additional measures of the same construct and also not related to measures that are not related to that construct? One of the final things I wanted to review is validity generalization, often referred to as VG in IO psychology because we like to abbreviate things. And this is the extent to which a test found valid for one job in one location is valid for the same job in a different location. And validity generalization is very important for two main points. The first one being a legal point. If there is ample evidence or inference of validity that a test is valid in multiple settings and multiple organizations, it's usually easier to defend the use of that test in a court of law. The second part that's important is the actual process of how do you generalize and find out if a test does generalize in multiple settings. And this is a good example of science through replication. The way you do it is that you test that particular construct measure in multiple organizations, in multiple places, for multiple jobs, across multiple geographies, and even with multiple groups. If you find strong evidence that those correlation coefficients stay the same across all of those different settings and different people and different groups and different jobs, you've got strong evidence for validity generalization. If you find that it differs based on who's taking the test, where the test is being given geographically, or the type of job that's being tested, that's more situational specificity. It says that a test is valid for some situations in some locations and some jobs, but it's not automatically appropriate in other locations. In other words, this is a test that needs to have local validation studied anytime it's going to be used. So when we're doing a validity generalization test, what we're basically wanting to do is parcel out two major pieces of variance. We want to ask how much of the criterion is being predicted by the construct test across multiple studies. So again, if we're doing validity generalization, we are comparing multiple studies that looked at different cultures, different geographic regions, different job titles, different job descriptions, but always using the same measure of a construct and always matching it with a criterion, generally performance. So we want to parcel out two pieces of information. First, we want to get what is the average amount of performance that is being predicted by this particular construct measure. The second thing we want is how much variance is occurring not due to variance between that construct and performance, but actually is due to the error of different samples, different places, different measurements, different geographies. So a validity generalization study is going to basically statistically separate out how much variance is being explained by our predictor, the construct we're interested in across all these studies, and how much variance is not associated with performance and the criteria and the predictor at all. It is simply variance based on the fact that we're doing studies in different locations with different people who are going to vary. So the statistical artifacts is the second thing that we care about. We care about the overall relationship between our construct, this measure that we're trying to validate, and performance across all these studies. And we also want the variance of how much of the variance across these studies is being explained by the differences in the studies. And those differences can include sample size, the reliability of the criterion, in other words, how they measured performance, differences in test reliability. So the exact same test will come up with slightly different reliability information in each new sample. Differences in restriction and range. So in some studies, we may be looking at the relationship between our predictor, the construct we're interested in measuring, and an outcome, performance, where everyone's a top performer. But in another study, we might be looking where everyone's a bottom performer and needs to be fired. And in another study, it might be more variance, where there's both top, middle, and bottom performers. Differences in criterion contamination and deficiency, so the quality of the criterion, how performance is measured. In some studies, performance may be a 1 to 4 rating given by a manager. In another study, performance may be hard objective data like actual performance figures or sales figures. And in another one, it may be 360-degree evaluations. Again, how much of the variance between the successful prediction of performance by our construct that we're interested in is not being explained by the actual relationship, but explained by simply the difference in the predictor used. any computational, typographical, and transcription areas, and also slight differences in the factor structure. All of these are quantified in all of the studies, and then we use that information to generate these two pieces of information. How much variation is due to changes in the study, and then after you account for that, how strong is the relationship between your measure and the performance measure or criterion across all those studies. So the steps in validity generalization mirror a lot of what we've been talking about, always starting with a job analysis for each study, identifying what the predictor and criterion should be. So what exactly are you trying to validate and generalize? Is it general cognitive ability? Is it personality? And what criterion are you trying to predict? This then creates the information you're going to use to determine what literature you need to review. And remember that this is kind of like a meta-analysis or a large lit review, in that you're going to now look at the successful relationships that have been found with your predictor and the criterion across many studies, looking at different samples and different groups. You want to reject situational specificity. So what we're looking at is a validity generalization study is asking a single hypothesis. Does this construct generalize in its validity of predicting performance across all locations, or does it need to be tested individually in any location? So the first thing we need to do to be able to reject situational specificity, in other words, say, yes, this measure does generalize across locations and jobs, is that if the statistical artifacts themselves, those are all those differences between the studies, are accounting for at least 75% of the unexplained variance that isn't being predicted by the predictor and the criterion. So validity is generalized if the confidence interval is around the mean is positive and does not include zero. So the two things we're getting is these last 2 points. When we run a validity generalization study, we want to measure how much variance is being accounted for all the differences between the studies we're comparing. That's point 4. And the last point, we now want to actually calculate what is the average validity coefficient between our measure and predictors across all these studies. If the interval, the confidence interval around that averaged mean is positive and does not include zero, then those 2 steps mean we have generalized that validity. So let me talk about this for one more second. This means, for example, that if the mean coefficient between our predictor, the construct we're interested in, and performance is 1.0, so that's 100%, but the confidence interval is 1.15, that means that though we calculated a mean of 100% prediction, the real mean could lie anywhere between an unreasonable 2.15 coefficient, which couldn't exist, but all the way down to a negative 0.15 coefficient. That means that the range of the confidence intervals includes zero. That would not be a generalizable coefficient. We couldn't say in all situations this generalizes. What it means is that in most situations it generalizes very well, but there's a few situations it doesn't. More reasonably, we might find that the validity coefficient mean, again from all these studies, might be an R of 0.30, and the confidence interval is 0.05, which means that the mean across all these studies of the actual relationship between the predictor and criterion is somewhere between 0.25 and 0.35. It's positive, it doesn't include zero, we have validity generalization, as long as the actual statistical artifacts are accounting for at least 75% of the variance. You need to meet both of these. Now, you will occasionally run across a validity generalization study that fulfills the last requirement, but does not necessarily account for statistical artifacts of at least 75%. This is a rule of thumb, and some people will play a little fast and loose with it. So again, this is getting to that idea that the higher our validity, the better the relationship is going to be between the criterion and the predictor battery. And the more accurate that is, the less misses and false alarms we'll have and the more hits. The tighter the validity, the more it's actually predicting what we think it's measuring. We're going to see a stronger R, we're going to see less error, and we're going to be more accurate in being able to predict. And the weaker the validity, the less successful we are going to be at prediction. And of course, a completely invalid test is the same as flipping a coin. There's no advantage to using it. So the last actual article that we didn't get a chance to go over was Saldego et al. 2003, and basically it's an example of a validity generalization study. And I just want to point out a few things that kind of highlight what we've been talking about in this audio lecture. And that is that what they looked for was general mental ability, so general cognitive ability, and they were looking at both. There's already been meta-analyses that have looked at the U.S. that have basically validated and generalized the validation, so validity generalization studies that have shown that cognitive ability is a good predictor across almost all jobs in the U.S. So what they were wanting to look at was specifically, is there a difference then between the US and the EC? So they did a test of basically a meta-analysis looking at the European Union, the European community, and they did indeed find further evidence for the validity of generalization of GMA. In fact, they actually found that it was a little bit more predictive in Europe than it was in the United States, and they kind of talked a little bit about why that might be, including, again, some of these statistical artifacts. So how performance is measured, for example, in Europe, where it's more likely to be a single subjective rating compared to the US that tends to be a little bit more likely to use objective ratings. Now, if you look on page 586 of the article, you can pause the recording right now if you want to get that out. But I want to point out to you a few of the things we were just talking about. So on page 586 is table 5. And if you look at the very top horizontal line, you see GMA. So the first thing, if you go 3 over, you're going to see an R of 0.29. That's actually the average of how well it predicts across all these studies. So that's what's saying that overall cognitive ability in the European sample is predicting performance with an R of 0.29. So again, 0.29 times 0.29, a little under 9% of the variance explained. If you skip on over a few more, you're going to see percentage of VE. So again, that VE now is actually variance accounted for by the artifacts error. So the error that was attributed to the different types of studies. We've just squeaked across the line here. We see 7.5. So 75% of the variance is actually being explained between these studies. In other words, it's saying these studies are finding vast differences. How successful GMA is at predicting performance does vary across studies, but most of that variance isn't about the relationship between cognitive ability and performance. It's about all the differences in the studies. So that's good as well. And finally, getting to that idea of plus or minus, that the mean is within 0. If you look at LRHO, the third to last column, and LCV, if either of these were negative or 0, that would indicate that we are not confident that that mean is the same. So if you look one column down, let's look at verbal. Going over to the third column, R, you see that verbal is related 0.16 across all studies. However, the VE, percentage of variance explained by the artifacts, is only 53%. So that's starting to indicate that there may actually be some areas where verbal intelligence does not necessarily predict performance in some studies. If we look at the LRHO, 0.32, good. But if we look at LCV, 0. In that case, this indicates that there is some studies where actually verbal does not predict performance at all. And this would be an indication that at least for verbal intelligence, we have specificity in our generalization. You need to validate that based on the study or based on the job that you're looking at and based on the location. But general mental ability passed the test. It has been validated to be valid across all of the studies that we looked at. I hope this was helpful to you, and if you have any questions, please let me know.